kinds of page ranks that can make the page rank be more and more customized to the user, right? Because after all, we need to support the importance measures with respect to the user's interests. And that's basically, who that is. He was asked one time, I think recently, whether he had any focus groups before iPad was brought into the market, and he said, it's not the consumer's job to know what they want. So he will tell the consumers what they want. So I was thinking we should have had a Steve rank as against page rank, and that would have been much easier to describe. Essentially you send your query, Apple throws it out, and Steve Jobs tells you what you should be finding out about. Anyway, so for today, we are going to be talking about the engineering issues in the search engines. In particular, there is a part about crawling, which is, unlike standard IR, essentially the search engine has to go all over the web and get the pages first before it has a corpus of pages, right? So we'll talk a little about crawling, and then we'll also talk about the fact that essentially most of the tasks that we have discussed till now have to be done at very, very, very large scale data. Okay, so you're talking about very large multi-terabyte files on which you have to do the computations. The computational tasks themselves are very simple. It's the input complexity that matters. It's the size of the input is very large, and then you do little computations for each element of that file, for example. Okay, and unfortunately, that sort of a thing is not particularly well suited for single CPU machines. And so this is not the first time you heard about it. There are server farms, and there is a particular kind of coarse-grained parallelism that is very useful for these kinds of tasks. It's been called the MapReduce parallelism, and we'll talk about MapReduce architectures a little. And in particular, that's what I asked you to read, the MapReduce chapter. It's an engineering section where really, this is not a course on architecture, right? So I can't give you all the systems details, but I do want you to understand what sort of architecture do you have to have in mind when you're thinking of writing an algorithm for one of these tasks. And in particular, you need to be able to write any task that you want to do. You need to have a MapReduce version of that task. Okay, till now you didn't care about what is the best way to write that program. You just talked about the algorithm. Okay, the question is, to the extent all the parallelism right now that's being supported is this MapReduce parallelism, and we'll see why they have chosen that kind of a parallelism to support. There's a good reason for it. Then the question would be, how would you do efficient anything on MapReduce parallelism? And in particular, we'll look at indexing and link analysis. In general, essentially, in fact, there should be a separate course on doing programming on MapReduce. And if you were to do that, then search engine companies and pretty much everybody who has large-scale data now and have to do small processing, small identical processing on gazillion billion copies of the similar types of data. They would all be very interested in that sort of program. Okay, so that's basically what I'm going to be doing today. That's the class. Are there any questions before I start? You don't want to know when the exam is going to be? Just want to keep it quiet. So if I don't say anything, you won't say anything. So I said it's going to be on next Thursday or the Monday after that. Those are the two choices. And my inclination right now is to make it not Monday, but Tuesday after that. So either next week's Thursday or Tuesday after that. My inclination is to have it on the Tuesday after that, but that's because I have homework to part B, which is going to be assigned as soon as this class is over, and it will be due on Thursday's class. Okay, and what that is that think of that as either appendage of the homework or the beginning of the exam. It is essentially reading the classic, quote unquote classic, for this class at any rate, the Google paper, which was rejected from multiple places and finally did appear in World Wide Web Conference in 1998. Okay, it's easy to read. There's not too much math in it, and you can essentially understand it as you're reading it right now. Okay, so I will send you a link, and I will essentially tell you it's a reading comprehension homework. Now, of course, the best way to do reading comprehension homework is to say you read it, and then I just believe you that you read it, which would make me a popular teacher. So if you look at it, this is the question that I'm going to make. Okay, so you read that and you answer all those questions, and all of those questions are essentially, if you read that paper, you would know where they are, what the answers are. Okay, so that's the idea. Okay, and by Thursday, the weekend is free and nothing to do. So you read that over the weekend, and it's good timing because essentially we are ending the discussion of search engines. Okay, and so it's a good way to. And there are not that many papers that have end-to-end description of a search engine implementation. The one that you're going to read is a 1998 paper. That's not the paper. I mean, that's not exactly describing what any of the modern search engines are actually doing, but it gives you a better idea than looking at different pieces in terms of what are the integration issues. Okay, and in particular, you can see what engineering decisions they made. Okay, so there is a difference between understanding how stresses and strains and trusses work out and building Brooklyn Bridge. Okay, and Brooklyn Bridge was built before people knew exactly whether or not, what are the kinds of forces are in operation. And people were building stuff before they knew what are the right ways to do it. And so, analyzing. So what we did actually is we did the analysis first. Now you want to see when they did one end-to-end search engine as a graduate student, as a pair of grad students, what corners did they cut? Did they cut them in a reasonable way? Would you agree with that? Okay. So it's a fairly interesting read. It's, as I said, basically because you know pretty much everything that is to know beforehand, before you read that paper, so you should be able to get it. Okay. So that's my, that's what I'm going to do. So I'll put this up into the other page so that it becomes officially part of your life. And then, and then on Thursday you will give me a page with the questions, answers to those questions. Okay, and then we can also discuss a little on Thursday if there are questions. In the old days, I used to have like a whole class just discussing that paper, but then I found that only I read the paper, and nobody is anyway has read it. So this is a way to make sure that you actually. Okay. So and then the exam would be Tuesday after next week. Okay. Okay, so what I'm going to do is, today's would be a lightweight class, mostly because it's just at least the, some of these things, it's like descriptive stuff. You need to know, but there isn't much I can prove about whether or not this is the best way to do crawling. Okay. So anyway, so let's talk about crawling. So presumably you realize that Sushovan crawled and gave you the pages so that you were actually doing traditional IR. Okay, so what you have to do if you're actually writing a search engine is you need to crawl the pages and then crawl all the content on the web and put it in some place so that you can then index it. Okay, so you need the question then, and also it's not a one-time job. You have to continually keep crawling because web is always, it's always evolving, and so you keep crawling. And so the question, of course, is what are the reasonable ways to do this crawling? Okay, that's what we're going to look at. So in particular, you have to think in terms of like you have like it's a sort of a search sort of a scenario where you have a queue of pages to be crawled. You pick a bunch of pages from there, you crawl. That means you go to those URLs, get the entire page into the into your processing, into your cache. Okay, and then when you're bringing that page in, you get new URLs which this page is pointing to. So those become part of the queue now, and then you have to pick some of those also and then go there. Right? So that's basically the idea. The question, of course, is the kind of search strategies that you've already heard of, all of you heard of in data structures, and some of you have heard of in other courses too, are things like breadth first, depth first. Okay, that's not particularly interesting in this case. In fact, you might want to have some sort of a prioritized search where certain pages get crawled more often than others. And so we'll try to figure out what would make reasonable metrics for deciding what is the importance of a page for its crawling priority. Okay, so that's and then so you would have to look at what page to go next, and of course one of the issues that you're interested in is making sure that this was probably sort of true when search engine started, and it's really true right now. If Google crawler takes a sudden interest in your site and thinks that you are particularly important and need to be, and they need to keep track of millisecond by millisecond changes in your site will go down. Okay, that's basically denial of service attack, without saying it in so many words. And so what they need to do is they have to essentially, to make sure that they won't get into trouble, they have to have some sort of politeness constraints, not more than so many hits to the same server, under a certain period of time. Okay, and then how deep would you drill down? These kinds of issues you have to look at. And the other thing is how frequently to visit pages. And there are many small issues which won't really require a humongous amount of discussion in a classroom, but they're still important. So for example, if a page basically sets up a very nice circular list of pages, then would you just keep getting stuck in it? If you do, depth first crawling, then you will never come out of it. Now you can say, well, it's easy to not get stuck, but at the same time, that's is something that you need to take into account if you're writing a crawler. In fact, the point is, writing a trivial crawler is trivial. Okay, that's the problem with all of engineering. Building a kind of a bad bridge is easy. It's like building a bridge that will hang around for generations is hard. Okay, writing a crawler is easy. Okay, writing a robust crawler which won't keep falling down is hard, and and most of the techniques that are involved don't require proofs, but you do need to consider all these small issues. Okay, so that's the basic crawling stuff. I mean, by the way, in the paper, so this discussion is actually from one of the oldest crawlers called the Mercator crawler, which used to be the crawler for Alta Vista, which most of you probably don't know. Alta Vista used to be the search engine before Google came along. Okay, and that was a Tech Western Research Lab search engine. And so Mercator was their crawler, and they wrote a nice paper about how their crawler works. Okay, however, that's what I'm kind of discussing in this stuff, but I also have a link on the readings to a paper that's a much more recent paper, recent in the sense only 3 years old paper, on what is involved in writing a state-of-the-art crawler. And it's worth reading if you're interested in knowing the issues. Okay. So anyway, first thing, of course, is there is this idea called robot exclusion, where you can essentially put on your if you have a website, on the top level of your website, you can put robots.txt, which is a sort of a convention wherein you get to say, tell the crawler, please leave this subdirectory alone, and please go only down to this subdirectory, only so many levels, and so on. So you can tell the crawler what to do. Now obviously, since the crawler does not owe you anything, right? So in some sense, if you have put passport information and social security information in this particular folder, you tell the crawler, please don't do this because this is where all the important information is. And you know what happens. Next day in the front page, your passport information will be there. So the point being that robots.txt is a voluntary protocol. You get to write it, and major search engines probably don't want to be shown to be intentionally violating it, just because people will write bad articles on them. Minor search engines don't care. Any publicity is good publicity, right? And so, in general, keep that in mind. But essentially, if you were to agree, if you were to be, sort of gentlemanly, gentlewomanly in your conduct in crawling, then you will follow these rules. Okay? If people write it, and so it has some, syntax. So, for example, if you want to exclude all the servers, you can also, for example, say, I only want to be crawled by Bing, not by Google. So you can say that. Okay, so it basically robots.txt allows you. They have a syntax whereby you can say which crawling agents are allowed to crawl what parts. Okay, but then as I said, this is just a voluntary protocol. People don't actually have to follow it. Okay. So that's one thing, that's a useful thing that people can put in their websites. And then normally, if you are writing a legal crawler, it is supposed to first go to the robots.txt and then see what it is saying and then follow the rules. Okay? Anyway, so that's first thing to keep in mind. So in this case, for example, saying web crawler was an old agent. It's like nowadays it's Google bot or Yahoo bot or whatever. So it's saying for web crawler, it should not be crawling /news subdirectory and /temp subdirectory. That's what it's saying. Okay. If you're interested in full robot.txt protocol, you can look it up pretty much anywhere. So here is like a sort of an architecture for the Mercator, original Mercator crawler that they wrote papers about. And here are the steps in it. So you remove the URL from the queue, you simulate once you got the URL, you need to actually simulate the protocols to, HTTP. In fact, one of the interesting things is, at the time this Mercator was written, it was still not completely obvious that HTTP would be pretty much the only main protocol. So this would be supporting FTP, Gopher, and all these other protocols too. Okay, but nowadays they are still there, but much less. So if your crawler doesn't support Gopher, for example, it's not really going to be a major issue. Okay. So you do the protocols for the network, and then you get to the page, okay, and then bring the content of the page. And the next question is, have you seen this document before? Okay, why is this important? If you have seen this document before, there is no point in putting all the URLs from this document back onto the queue, because that would be duplicate URLs. Okay. Now the question, of course, is how do you find that? This is basically where you don't need to do real duplicate check. You do some sort of a checksum check. Okay, so you compute a checksum for the a fingerprint for the entire page, and then you have a hash table full of the pages which you have already seen before, and you see if the fingerprint matches, in which case you basically not go further from that page. Deciding not to go further from the page essentially means not putting the URLs on that page into your queue. If you don't, then you would not be following that page any further, because they must have already been on your queue. Okay? Then if not, then you extract the links, and then here again too, essentially notice that it's easy stuff to say, but people will write links sometimes in absolute form, sometimes in offset form, and so if you are putting it in a queue, you need to make sure that every link that you put in is an absolute link. And so if it's an offset form, then you need to make sure that it's not offset. Okay. Now this is not going to if you don't do it, essentially, you will get a bad crawler, which just sort of misses most of the links. But not doing it is not too hard, but not if you don't do it, you get in trouble. And then having gotten the URLs, then the question is, has this URL itself been seen before? Right? Because multiple people might be pointing to this URL. If so, then it must be already on your link in a queue, in which case you don't need to put it in. Okay? If it hasn't been seen before, then you just throw it to the frontier. Frontier is the queue of all the links that you are about to crawl. Okay? So the question then is, the big question would then be, how do I remove a URL from the queue? Okay? That's the issue. And the assumption is that you want, this was probably then, but nobody really uses breadth first. And nobody certainly uses depth first, because depth first is a killer. You can go into cycles. Okay? So what you would like to do essentially is some sort of a priority-based queue. Okay? Where each URL is given a priority, and then you pick the URLs with high priority from the queue. Okay. Now, the one question, of course, is that just because a URL comes up high doesn't necessarily mean that you should send your entire, especially given what we'll be discussing next, which is, most of these servers have many server threads. So they can all hit your page at the same time, and your page will come crawling, crashing down. So you need to have politeness constraint. Basically, even if they don't care about your site and it falling down, if every site you try to go to falls down, then your crawler is not going anywhere, right? So it's also kind of from your selfishness point of view also, it's not a good idea. Okay, so sort of you need to take into account the politeness, which means you need to keep track of how many, what was the last time you went to this particular site. And then not go back to that site too often. Okay. Now here is one example. This is not necessarily, again, there are many implementations of crawlers. Google writes that paper that you will read. They will tell you a little about what crawler they wrote when they were grad students. The current Google, who knows what it does. Okay. And then there is a paper I told you which gives you a much more recent version of a crawler, at least from an academic side. But here is an example of a reasonable way you can do this. Here you have a bunch of priority queues. Okay, each priority queue. So this is priority 1, 2, etc. up to k. And I can assume that the higher the number, the more higher the priority, for example. You can decide whatever. And so from these queues, then the idea here is that you will tend to pick randomly from one of these queues. Okay? But the random selection is biased towards higher important queues. So you tend to pick more often from this than from this. Okay? But none of the probabilities are 0. So that means there is no starvation for any of the queues. Okay? And so of course, as the URLs come in, you have to prioritize them and put them into these queues. The more important versus less important queues. And then having gotten them, then when you pick the URLs to be crawled next, and these essentially are other backend queues, where what these are doing essentially is they're making sure that for each important site, let's say CNN, there's going to be a queue of all the URLs from CNN that you're going to hit, and all the URLs from NY Times you're going to hit, and so on. And the idea then is these you would do round robin, so that after one CNN you do one NY Times, then one something else before coming back to CNN. Yes?
This might be a dumb question, but if you're going to hit all the pages, why do you care about the priority?
The question, okay, so it's a very interesting point, which is, first of all, you never done. On the web, this is a continuing process. The crawling is always going on. Indexing is always going on. Okay? And so, really, you want to make sure that all the important pages are sort of, crawled more often. Okay? Now the question, of course, is what are important pages? So that's my question. So how do I prioritize the pages?
Depending on how fast they change.
Depending on how fast they change. Is that the only thing?
Importance.
Importance. So basically you want, those are the two things that you need to consider. So you need to consider the importance of the page to begin with, okay? And you also want to consider how fast does the page change, okay? So for example, you know, a page in National Archives giving the US Constitution, I would assume is important, but you don't need to crawl it every day. You see what I'm saying? It takes forever to change the Constitution. And so you don't need to worry, right? So here is a situation where it's a very important page. You know, lots and lots of pages will be pointing out, especially all the grade school kids will be reading that page to figure out what US Constitution is. But you know, Google or any search engine doesn't have to keep crawling to see if they have kept changing. Okay, so that's a good way to remember that in crawling you also care about the change rate. But it's not just the change rate either, because some nameless page that keeps changing you don't necessarily care. Okay, so those two at least have to be taken into consideration, and so now you have to put these apples and those oranges together to come up with a priority metric. Okay, so that's the basic idea for that. So change rate and page importance at least. Okay. There can be other things you might be able to think of, but you know, those are the important things. Okay. One other, okay, that's fine. This is just saying these are simple ideas. Fetch pages, you know, if you're trying to fetch pages, then you need to consider doing some obvious steps such as, you know, DNS lookups and doing, you know, actually simulating the protocols and so on. None of which makes for interesting lecture material here, but if you don't do it, then your crawler won't work. Okay. And then this one, how to extract URLs from a web page, again, it's boring stuff, but if you miss a few, then you don't have those URLs extracted. Okay. So you can see, as I'm saying boring stuff, etc., that I don't go around writing crawlers, so I'm not showing my enthusiasm for writing crawlers to you. So you should, you know, despite my enthusiasm for, or lack of enthusiasm for engineering issues, you should have it, because otherwise you won't be able to. Okay. The duplicate detection we talked about, essentially you need to have some kind of a signature for each page. Okay. One other thing, so that's all I actually want to say about crawling, really. Okay. Not much more than that. The one other question about crawling is the crawling for the entire web, or is it for some sort of a vertical search engine which is only about a specific topic? Okay, so like today, let's say you want to write an engine which basically does computer science papers. It wants to crawl and keep all computer science papers. And then you want to support analysis on just them. You couldn't care less about the rest of the web. Okay, so how would you go about crawling for your search engine? Now, if Google were to try and do it, Google or Bing were to try and do it, what would they do? They take the crawl they already have and filter out the non-computer science stuff. Much simpler. But you would not have to crawl the entire universe to just get the subset you're getting, right? So, an interesting question that's sort of not an issue for mainstream search engines, but it's an issue if you are writing a vertical search engine for yourself, is how do you crawl such that the URLs you are crawling are likely to be relevant to the topic that you are interested in supporting. Okay, and that's basically called focused crawling. Okay, and it's a kind of an interesting question because before you go to the page, you need to know whether it's worth going to the page or not. I mean, after going to the page and noticing that there is nothing about computer science on it by basically comparing its text to some computer science bag of words and finding that there is, you know, the vector similarity is very low, you can give up at that point. But then you wasted all the time already. Right? So there is some work that's been done in the past. I don't know that it's still useful if you're writing your own vertical search engines, which basically tries to tell you for a given URL whether or not it's likely to be relevant to your topic. And in some sense, it's a machine learning problem. It's like a classification problem where just like you're classifying mails into spam and non-spam, And so remember this when we get to text classification, which is after the midterm. But here you are trying to classify each URL into would be relevant to my topic, won't be relevant to my topic. Okay, and then based on that, you would decide whether or not to go. Okay, so I won't go into major details on this, but there is that sort of an issue that this is not a problem faced by mainstream search engines because they already have the full crawl. They just can take the subset they want. And you are trying to avoid doing the full crawl and still supporting search on your topic. Okay. So that's the issue on that. One other thing is, actually this could come anywhere, but one thing about PageRank, actually this should have come before PageRank, right after PageRank, which is that just as you have inverted indexes, where given the word it tells you where are all the documents, you also need backlink structure. After the crawling, so once you crawl, essentially, it turns out that once you do crawling, then two phases are done after the crawling. One is indexing, I mean at least two parts. One is indexing, and then the other is this computation of the connectivity server, which is also an inverted index, which basically says, given a URL, what are all the other URLs from where there are links to this URL? The forward one would be, if you are in this URL, what are the pages it's pointing to? That's easy to know. The backward one is, given a URL, what are all the links that are coming to it? Okay, and it's this connectivity server that you are using in your PageRank computation. Okay, so it's worth remembering that essentially these two, everything you know about it, inverted indices works here too. Okay, and then a little later in today's class or beginning of next class, we will talk about how to do efficient index construction on MapReduce architectures, and that discussion would be done with respect to words, inverted index of words, but it also could work for this. Okay. Yes.
So I was just wondering that if I have a page that I post as GoDaddy or something, and if I do not link to any other pages or no other pages actually link to me because I don't need to do it, then if I do a Google search, the page doesn't show. Is it because it is not being detected by the crawler, or because previous class we learned that if it is isolated from the major links and the major pages which are linked to each other, it's harmless or authoritative?
So this is a good point actually. I mean, we didn't talk about this. So in some sense, what I showed you is, the way I showed you, if you start with some set of pages to begin with, then if nobody from that page, those pages, or the descendants of those pages are pointing to you, then as far as link traversal is concerned, you cannot be reached. And so you won't be crawled. Okay? By going on the links. But search engines, the current day search engines do all sorts of tricks, including, for example, trying to see if there is something there. Okay, so I mean, how hard is it to actually decide whether or not there is a server at a particular URL? You just need to, get the IP address, and the IP address has significant amount of, IP address is just these 4 fields. Okay, so you generate random IP addresses and check if there's something there. If there's something there, then even if nobody is pointing to you, you still got caught. Do you see what I'm saying? So those sort of techniques have to be used if you went on the web and made sure nobody is pointing to you. And then, of course, there are these assumptions that there could be clusters on the web that don't want to be detected, and so they only point to each other and nobody from outside. They don't allow. Nobody from outside point to them. First of all, you don't have, any control over what other people do to your page. Okay. But suppose nobody is pointing to you, then all I need is, by trial and error, if I found one of these hidden pages, quote unquote, okay, then I found the entire cluster. Because then from that I can start following links. Okay, so that is done. I don't have specific techniques that I can say are being used by search engines, but in general, That's one way you make sure that you get to all the pages, even if nobody is making any links to it. Okay? And that's obviously that's an inefficient way because there are just still too many web addresses. And so you can do it a better way. So most of the web probably is being pointed to by somebody else on the web. And so that stuff can be found by normal crawling. And then you have to have some global way of catching the ones that are calling. Okay. Any other questions? Okay. So next thing I'm going to do today is this MapReduce stuff. And again, it's a systems class right now. Basically the idea is that you have large web files that you need to process because if you're thinking of computing the inverted index for the entire web, that's going to be a huge file. Okay, and so processing that on a single CPU is not going to work. Okay, and the other issue, of course, is that fault tolerance. You want your search engines involved, basically. Again, so there are a bunch of things that come together here. There's the notion of cloud computing. Okay, and there's the notion of MapReduce, parallelism. And they have some common motivations, but we will get to it from the MapReduce side mostly. Okay, so the basic idea is that you need extra CPU power, but rather than buy very fast CPUs, fewer of them, you want to buy many cheap CPUs and let them do small computations. Now, this would work if in fact the kind of computations that you want to do. So I can have two computations, okay? Two computations, both of which take on a single CPU 10,000 hours. Okay, and one of which can be done by MapReduce because in essence this 10,000 hours is repeatedly doing very small computations on humongous number of data. So for example, what happens in inverted index computation? You look at the document and for each word you find, you will say word occurrence, word occurrence, word occurrence. And then you put these word occurrences together to compute how many occurrences of the word are appearing. And then you compute the inverted index. Each individual computation isn't really a very hard computation. It's just that for each entity you need to do that separately. Do you understand what I'm saying? So if I have to shake each of your hands, then it will take time. Do you understand? I mean, all I need then to speed it up is to clone myself so that there are as many of me as of you, and so each of my clones will shake each of your hands and we are done. Okay? Now, if on the other hand, so that kind of a parallelism is much simpler because you can basically, these clones don't need to know anything other than shaking hands. They could be really cheap computers. Okay? On the other hand, you could also have a $10,000 computation which cannot be parallelized that way. Okay? In which case, then essentially I would need to speed it up. I would not be able to just get clones of me which only know how to shake hands, but I need reasonably, I guess I don't want to get into this issue, but for the computers at least, you might need more, powerful computers. Each CPU might need to be more powerful. And so that requires essentially your Cray computing, for example. How many of you still know about Cray supercomputers, for example? Okay, that's the kind of thing where you need supercomputers. Okay, so this is a coarse-grained parallelism. So basically the parallelism here is each individual CPU is doing a very cheap task. And you just need a whole bunch of those CPUs doing that for a whole number of people, whole number of these data elements. Okay. So to the extent your tasks are of this type, then you can get by with architectures where you have a huge number of cheap machines. This is the server farms. You have a racks of cheap machines, and then essentially there is a master controller on top of these racks of cheap machines, and then you're somehow trying to use. This is like a brain for hire, not particularly genius quality brain, I might add. Okay, it's just a brain for that. Okay, the example that I actually have in mind, which I think is better than my teacher example, is suppose I need 10,000 hours of research to be done. Okay, if I'm in the biology department, right, then I would have, maybe that's because I have 10,000 these glass plates with some stain on them. And then I just need 10,000 undergrad or high school students to put them under 10,000 microscopes and stare at them for 10,000 hours, 1 hour each. And they all get to feel that they have taken part in research, right? And they get to write on their CVs that we helped, this professor with biology research, right? And I get my work done, okay? Now, if on the other hand, I also need a different way of 10,000 hours of work done. I just have this idea for proving P equal to NP. Okay? And I just need, I think I have this feeling that it will take 10,000 hours of work to figure out whether or not this proof is going to work. Okay? It's a very different kind of situation. Getting 10,000 high school students or undergrads or even grad students is not going to help. In fact, I'm going to waste my time saying, quiet down guys, quiet down, let's think now, right? And that's why you don't see too many students saying they have this, what?
I'm only for 1 hour.
1 hour. Okay, in most of them, even if 10,000 of them spend 10,000 hours each, we may still not get anywhere because the CPU is sort of faulty, right? Okay, and so what is happening in this case is that there are like two things are happening. One is sociological, which is all high school kids, and this is my pet peeve, think that they are interested in biology. Why? Because they have done biology research. Why? Because biology research is MapReduce kind of research. Huge number of small CPUs can feel as if they are taking part in biology research by looking at these classes. And I'm unable to come up with. I would like to have my research also be MapReducible. Okay. Wherein I can take 10,000 or even 10 undergrads and make them parallelly do some piece of my research, and they feel good, I feel good, NSF feels good, saying Rav is actually supporting undergraduate research. But it's not that easy. Okay, and if I'm having trouble, then God help the guy who's trying to come up with proofs for one of those millennium problems, right? There 10,000 doesn't matter. It's just one CPU working deeply, what matters. Okay, so thank goodness that most search engines do biology kind of work, okay? Because most of the tasks that you have can essentially be done as small, repetitive computations on different elements of it. And the other interesting thing is that now that there are enough such as, you understand MapReduce, now you understood MapReduce, you generate a whole infrastructure for MapReduce computations. Now that you have MapReduce computation, you have a hammer. For the guy with a hammer in the hand, everything looks like a nail. Okay, so you need to, if you want to use this hammer, you need to find for everything else you want to do, can you write it as a MapReduce computation? Although I won't be spending that much time on this here, in fact, a good way to essentially, be very helpful for all these big companies doesn't have to be just search engine companies, social networking companies, anybody who has a humongous amount of data, but mostly want to do simple, processing on each piece of this data. Is take each of these computations and see, can I express it as a MapReduce computation? So I will tell you in today's class or class next, I will tell you how to do, I think I said at the beginning of the lecture, but I would tell you how to do MapReduce computation for index construction and page rank computation. But everything else, you may still be able to come up with a MapReduce computation. Okay? Sometimes it's easy, sometimes it's not. Sometimes the task itself is naturally MapReduce parallelizable, sometimes it's not. Okay? So that's the deal about MapReduce, and all this is basically saying is that if you have never heard anything about disk C science, etc., machines, small machines can have the latency is mostly in disk C. Okay, and so that's the times that they're showing there. Okay, no, that's and then basically this one is just pointing out that most of these companies have huge server farms. Okay, and this is probably already old information. This is already outdated. In fact, today I was looking at San Jose MapReduce to find out more about what's going on Steve Jobs' thing, and one of their big articles is more and more server farms are being constructed all over San Jose area. In the old days, they at least would go all the way to Oregon, where nothing is happening, and then put up a server farm there. Now they're putting it also in San Jose. Okay. So there are a large number of these server farms that are being constructed where essentially we look at the architecture of them as the racks of cheap machines. Okay, and then some master controller basically saying who does what, and the master controllers are also replicated. Okay, so the important interesting thing about this is one other reason for this kind of a computational architecture is fault tolerant systems are very hard to get. Okay, so if you have 99% uptime and you have about 1,000 nodes, then your actual uptime is only 63%. Because one of them might fall down, and if any of them fall down, and if you make the computation be such that it's dependent on all 1,000 nodes being up at the same time, then you're dead. Okay, so even with independent failures, then you'll essentially have only a 63% uptime if each individual machine is 99% uptime. So whereas in the MapReduce kind of a scenario, what you would wind up doing is you don't depend on everybody being up at the same time. Okay. So if we have these cheap machines available, you can put them in the racks, and as long as they don't need to do fine-grained parallelism, where each machine needs to know what is in the main memory of the other machine, for example. That's the fine-grained parallelism. Okay. All they do really is sort of, each machine pipes its data to some central area, which is where the pipe data is then, reduced by some other machine. Okay. If you're doing that, then what kind of parallelism can you do? If you have multiple machines, it cannot be fine-grained because you don't have, inter-machine connection to the main memory itself. It cannot depend on shared memory. For those of you who know anything about parallel computation, this is like a big issue, which is whether the parallel computation model has shared memory or doesn't have shared memory. If you have shared memory, that means all of you are writing into the same memory at the same time. And then worker machines should be largely allowed to do their work independently. And if a worker machine dies, it should basically bring down the entire computation. Okay? And then furthermore, at the time you are writing your program, you may not even know how many worker machines would be available. And so there should actually be, the infrastructure that you have should be able to take this program written in this high-level language, and at the runtime, essentially schedule this computation onto the machines. There are more machines, more parallelism. Less machines, less parallelism. So if I have 10,000 undergrads coming to help me with my biology experiment, then I'll say, each of you look at one glass plate. If only 5,000 come, then I say, each of you look at 2 glass plates. If one guy comes, I leave the research area because both of you get bored. But the point is that I can decide, after seeing how many people showed up, how much work each of them have to do. Okay, the work itself, the program itself is run different before, but then you're scheduling it on time, at the time the machines come around. Okay, so these are the things that we are interested in, and this is where the ideas, an idea, but that sort of satisfies all these constraints is this MapReduce parallelism. So how many of you know where the words map and reduce come from? Yeah? Who else? Has anybody actually used MapReduce in their lives? Have you heard of Lisp? Undergrads have heard of Lisp, right? Lisp supports MapReduce, essentially. So in fact, that's the exact word it uses, MapReduce. And so I will show you some examples of mapping and MapReduce computations in this. Now, this is a higher level program language. This is just a language construct. Okay, so for example, the assumption in MapReduce computation is so Lisp and functional programming languages essentially can use functions as if they are data. Okay, and so you can say, take this function, apply it to this data. Okay, in the map part, what I'm saying is, map this function 1 into this list of data. So apply this function to each sublist of this list. And then what I will get out of the map is a list of processed data. Then the reduce part would apply a function to that entire list of returned data. Okay? As an example, suppose I have the list of data 4, 5, 6, 7, 8, 9. By the way, this is list. It's actually, if you have list running, you can type this in, it will work. Okay? And if I can say map function 1 plus, which is basically increment the number, on this list. And what it does is, it does the incrementing operation once for each of the data items. At the time map is called, it doesn't know how many times this function is going to be applied. It will run time, it will figure out how long the list is, and for each data item, it will do this function. Okay? So if you do this, then from the map part, you get 5, 6, 7, 8, 9, 10. Right? Because you are incrementing each of them by 1. Now the reduce part is basically saying, in this case I'm saying, reduce this list of numbers by the operation multiplication. That means multiply the first one by the second one by the third one by the fourth one by the fifth one, and then give me one result. So map basically has this field that you have multiple glass plates, right? So go back to my biology analogy. So I have these glass plates, and I'm looking to see how many glass plates have a particular formation, maybe some particular bacterium is supposed to be there. So I get all these 10,000 undergrads and say, all of you, parallelly look at the glass plates, okay? And any of you find this bacterium, raise your hand. And actually, I'll put 9,999, and then one extra undergrad would just count the raised hands. And then comes to me and knocks on my door and says, 5,700 people raised their hands, so there are 5,700 glass plates with the bacterium on it. So I got useful work from high school and undergrad students, right? Okay, so that's basically what reduce is doing. Reduce is just, map is doing the same computation on multiple pieces of data. Reduce is sort of putting together that. Okay, that's a MapReduce computation. Another example for here would be, if I have a whole bunch of numbers and I want to find out how many numbers are, prime numbers, right? I might check, I have a primality test, I map the primality test onto all the numbers, and then it will give me 1 or 0, 1 meaning it's a prime number, 0 means it's not a prime number, and then the reduce operation uses plus. Okay, now the reduce operation uses plus, then essentially I will just get the number of prime numbers. Now, this would allow you to use any functions, in the reduce and map. But think about the following question: would divided by be a reasonable operation for reduce? Would the subtraction be a reasonable operation for reduce? The reason they won't be is because multiplication and addition have this very nice property. They are commutative and they are associative. So the order in which my undergrads get done and raise their hands doesn't matter. And the order in which my, the master undergrad student counts the raised hands doesn't matter. The answer would be the same. Because plus happens to be commutative and associative. A plus B is the same as B plus A. A plus B plus C is the same as A plus B plus C. That's what commutative and associative means. Okay? Whereas that's not true for division and subtraction. Okay? That's not true for a whole bunch of operations in the world. Right? Okay? And so, in general, people, you would like to make your reduced computation be such that it is commutative and associative. Why? Because, just a second. Because even though in list, a single CPU is actually applying this primality test to each of the numbers. And the same single CPU is applying the incrementing operation to each of the numbers. So in essence, the operations are all going to be done eventually in a sequential fashion. Right? If on the other hand, there is no guarantee on which order the incrementing happens, which order the primary test is happening, and then similarly on this side, on the reduced side too, as the numbers are coming out of the first list, you can start adding them up. And what's interesting is that actually you can easily see that the map can be parallelized because each primality test can be run on a separate CPU. But I can also parallelize the reduce aspect. So in my biology experiment, I can have 4 undergrad students. And so 10,000 undergrad students actually spend time on their microscope. Okay? And 4 undergrad students, the first one looks at the first 1/4, second one looks at the second 1/4, third one looks at the third 1/4. And then adds up the raised hands, and then they add up their numbers and give me the final number. When that happens, you clearly want reduction operation be commutative and associative. Okay? Okay, so that's all this basically that slide says. The parallelism is that map operations can be done in parallel. You can test the primality of each of the numbers in parallel. The overall reduction operation has to be done after the map operation map gets done. But on the other hand, it too can be parallelized. So as the map operations, primality test results are coming, the corresponding reduce operation can start doing its work. Okay. In general, you expect to find that the number of machines, doing the map would be more than the number of machines doing the reduction. That was certainly true in my biology analogy. Okay, but that's not true in general. Okay, and then parallelism can be done, and both these cases have this very interesting property that the parallelism depends on the length of the input. The longer the input, the more parallelism you need. The more parallelism you can exploit. Do you see what I'm saying? If the individual computation itself, primality test itself takes a lot of time. So that itself can be parallelized separately. That's not what we were talking about here. Okay? Talking about how to write a single program that checks primality of a number fast using some parallel computing method. Okay? That's not what we're talking about. We're assuming each CPU still checks one number to be prime or not prime. And all I'm doing is then the number of such CPUs I need would be equal to the number of numbers I have to check primality. So this is the input-driven parallelism. Okay? And if you do that, then you essentially are in the MapReduce form. So a cluster infrastructure can then parallelize the map and reduce parts using the available pool of machines. So if you, in essence,